Hi, welcome to this organic chemistry quick video. This is alpha carbon chemistry part 2, enols, enolates, and amines. As we talked about last time, we split alpha carbons into two groups, carbonyls and everything else, and we're doing everything else, which is the enols, enolates, and amines. Well, an enol and an enolate, what the heck are these? Ene, alkene, ol for alcohol. This is what happens in the presence of an acid or a base. It doesn't really matter which one you have. You will end up plucking off of a hydrogen off of that alpha carbon that's circled in purple because you have the ability for resonance. Once you pluck off that hydrogen, you're left with a lone pair right next to a double bond, and that gives you your alkene. Then when you're plucking that off and you go through the resonance, pull down the double bond, you're going to end up with a negative O up there. That's called an enolate because it's got a negative charge. Add a hydrogen onto that and you end up with what's called an enol. So you can see that down at the bottom. The reaction between a ketone and an enol is called tautomerization. It's where two compounds have just the movement of a hydrogen, and it's kind of like a rearrangement idea. If you have an asymmetrical carbonyl, there are two different directions that you could go with your enol. Well, you're going to go to the more substituted side because it's more stable. You think about the stability of a double bond, the more things that you have coming off of them that are not hydrogen, the more stable it is. So you'll form the more substituted side. Enols and enolates typically form with ketones, aldehydes, carboxylic acids, and esters as long as you have an alpha hydrogen available. So that's what I'm showing here in this video. Don't worry, I'll show it again. First one's a ketone, second one's an aldehyde, next one's a carboxylic acid, and the last one is an ester. So the first thing that will happen whenever you have this going on is a base will come in, deprotonate your alpha hydrogen, which gives you your double bond. If you still have a negative charge, it's called an enolate until a hydrogen comes in, and you end up with an enol. Okay, so that's the general reaction that we're starting off with all of these reactions. You have to have the ability for this to happen. And the position that they're in right now is available for resonance. That's going to make that the alpha carbon position a lot more reactive because it has a slightly negative charge. These are the reactions that you can do. I'm not going to go over them each in detail, otherwise this won't be a very short video, but you can hopefully follow along. First one, you're replacing the alpha hydrogen with a halogen. Second one down, you're actually starting from the middle. This is showing on an aldehyde. On the right, you have a tertiary, left you have a secondary. Depending on what temperature and which base you're using will depend upon which direction it goes. The next one is a methyl ketone. If you have a methyl ketone, which means a methyl group coming off of a ketone, a strong base with bromine, followed up by an acid workup, will give you a carboxylic acid. The next one down is showing where you're actually combining two things. They can be aldehydes or ketones in order to form eventually the alpha-beta unsaturated aldehyde or ketone. Where it says beta hydroxy, that middle one, that is because off of the beta carbon, so the first one where you've got the green and purple R groups off, that's your alpha position. Beta position is next down. You have a hydroxy group. So it's a beta hydroxyaldehyde or ketone. And then the alpha beta unsaturated is because between your alpha and beta carbon, you have a double bond, so it's unsaturated. That's something that's very important. We'll show on the next slide. And then over on the right is a carboxylic acid halogenating just like we saw with the ketone. And Michael reaction. Look, there's our alpha beta unsaturated carbonyl. So if you react that with what's called an enolate nucleophile, and the squiggly blue and squiggly pink can be any of those donor groups down below. You can use the same on both sides, or you can have different on both sides. It doesn't matter. And there are others. That's just a good example of some of them. They will actually form a carbon-carbon bond off of your beta, and it's an addition across your double bond. Next one over, we've got the Stork enamine synthesis. Ene for alkene, amine for the amine group. Still working on your alpha-beta unsaturated carbonyl. Again, it's an addition across. Hydrogen goes up on the top on the alpha carbon, and then your amine group will add on to the bottom part, and it'll give you what's called a 1,5 dicarbonyl. Carbonyl is the C double bonded O. If you count the first one at position 1 and you get down to the second one, it's position 5. You can also do this on a specific type of your carbonyl enolate. So this is just like the Michael reaction, but it'll form a ring. It's called the Robinson annulation. I tried to color code those as best as I could. Any of those R's could be H's. The one that on the left-hand side for the carbonyl enolate, where between the pink and the blue, that has to be a hydrogen. The rest of them can be carbons or hydrogens. When we move on to esters, you can have what's called the Clausen condensation, and you can have Clausen condensation with a single ester where it adds onto itself, or you can have a mixed Clausen condensation where you have two different esters. Mind you, in order for you to have all four of these products, you have to have hydrogens in those positions. Okay, you have to have at least one hydrogen in the alpha position, otherwise it forces just one or two products. You can also form rings. You guys were hoping for that, I'm sure. So the decoming cyclization can either happen with a 5-member ring product or a 6-member ring product, depending upon the distance in between your two esters, but you do need to have two esters. Down below, I'm showing the malonic ester synthesis. You're not synthesizing malonic ester, you're actually using it. Malonic ester is that specific compound right there, CH3CH2O, CO, CH2, COO, CH2, CH3, and that will give you a carboxylic acid. If you have acetoacetic ester, which is that compound shown right there, it'll give you a ketone. Moving on to our amine reactions, these are all reactions that form amines, and we've done substitutions like that first one. However, I don't think I've ever showed you how you can hydrogenate it, and you can do that with an excess lithium aluminum hydride and water. Carboxylic acid, you have a similar thing going on where you're substituting out your OH group for an NH2, and then you're hydrogenating it, which will kick off your oxygen. Well, you have seen the benzene reaction where you're adding a NO2 group, but again, you can hydrogenate it, turning it into an NH2. Alkyl halides over here, instead of adding a cyanide, you're adding a N3. It's not coming to me. You're adding N3 to it, and then you're hydrogenating across it. And then the Gabriel synthesis, you can use different compounds, but that very first one that I'm showing you, the 2 rings, that's one of the more common ones, and that will also form amines. The reactions of amines, here we've got a couple of different ones. On the left-hand side, I'm showing you a primary, secondary, and then another primary kind of in a specific situation. You can literally just follow along with those. The top one on the right is forming a diazo, so you're actually forming a 2 benzenes across a nitrogen-nitrogen bond. Pyrrole and pyridine, good golly. Those are 2 different cyclic compounds with nitrogens in them. They kind of don't have another place to be in organic chemistry, so they're in here. Hope that this helps, and yeah, enjoy.